So I have an interesting problem today. So let's say I have with me a triangle. Oops, not a very good triangle. I'm going to draw. Yes, this is something that looks like a triangle. And I have with me three colors. I have the color red, I have the color green, and I have the color blue with me. I'm going to go ahead and color each of the vertex of this triangle with one of these three colors. So down here I have the red node, here I had the blue vertex, and now I'm going to color the green vertex. Okay, so I have colored this triangle, or rather the vertices of this triangle, with the three different colors. Now imagine if this triangle were made of glass, so it's a glass pane, and suddenly broke it. So what happens when we break a glass pane? Well, it shatters into pieces, right? Now it so happens that the way we have broken this glass plane, for the purposes of our problem, let's say that it has broken into smaller triangular pieces. So this is maybe an example of how the broken glass pane looks like. And these are the individual pieces of the shattered glass. And now, what we are going to do is we are going to color the vertices of each of these triangles. So there are so many vertices that are formed here, and we have to color them. Again, using one of these three colors. One vertex gets one color. Now, is there a rule for coloring? Yes, there is one, and there is just the one. So let's look at the edge of the original triangle. I'm going to call this edge right here, I'm going to call it the red blue edge. The only rule for this problem is that all the vertices of the broken pieces that lie on this red blue edge have to be colored with either red or blue. We can't color it with green. And similarly, for this edge, which I'm going to call the green red edge, all vertices that lie here are going to be colored either with red or with green and not with blue. And the same thing holds for this third one. So all none of the vertices on this blue green edge can be red. Let me go ahead and make a few colorings. So let me select the blue first. So maybe I can color this guy blue. And note that I'm doing this because this is a blue green edge, so I'm allowed to use blue here. And maybe I'll make this one blue as well. And then I'm going to make maybe this one green and this one green. How we color these vertices which lie on this outer edge is up to us. The only restriction is on the colors. So I'm going to go ahead and maybe complete this one. So I'm on the red green edge. I'm allowed to color vertices using only red and green. Okay, fair enough. There might be other vertices also, and just for this picture's sake, this is enough, I guess. And coming to the third one, so this blue red edge allows me to use only the blue or the red color. And I'm just going to be lazy and use red for the remaining two vertices. Nice. But if you take a look back, I see that there are still vertices in the broken glass pane pieces which lie completely inside. And then the problem tells us there's no more restriction. You can color each of the vertex which lies inside this bigger triangle any color you like. Okay, so I'm going to make this one red. Choose. Oops. Okay, so maybe that's not an issue. I can always create more triangles, right? So let me. This won't be a triangle. But yeah, let me make this. I'm going to maybe use red here. And just to make things clear, this one looks interesting. Yeah, I'm going to collect this and maybe use green here. Okay, I think this is enough to get the picture across. So there were only two rules. The first rule was how to color the vertices of the broken pieces on the outer edge. So we saw that that rule was, well, you look at the outer edge color. So by that I mean this edge right here is the blue green edge. So we cannot use the red color. So using that, we colored the vertices which lie on the outer edge of the original triangle. And then all restrictions were laid off, and we went inside and we just randomly colored all the vertices we found inside using any of these three colors. Okay, so now that's done. Now the question that is asked is this: irrespective of how we choose to color either the original triangle's edge, that's the coloring we started off with. We started off by coloring this red, blue, green. Well, it's a symmetric triangle, so that doesn't matter. And then we colored each of the vertices which lied on these edges of the triangle. And then we also colored the points which lied inside, completely inside this triangle. And none of these decisions were forced. We were the only restriction was that we use these three colors. And then this problem claims that no matter how you color following these rules, you will always end up with a triangle which has all three vertices of the same color. Let that sink in. Just think about it. So we have colored this thing with a very contrived way of coloring. Now, here is such a simple yet profound and non trivial claim. It says that there must be a triangle here which has three vertices of three different colors. And how do we go about showing that? And this has to be true for any way we color. So maybe we can either pause or reflect. Think about this. How would we even start solving such kind of a problem? Hmm, interesting. And this is what we do. This is how we proceed. So we have three colors with us. We have red, blue, and green. Inside my triangle, I will have smaller triangles, which are the pieces into which this glass pane has been broken into. And their edges might have different configurations, color configurations. One of the color configurations for one of these edges of the inside pieces, let's say it's blue red. And obviously it can be blue blue, red, red, green blue, and all the possible choices of two colors from these three colors, including, by the way, allowing repetition. So we are allowed to do blue blue. There's no restriction. We could have uh, just made this blue or this blue. No, actually, this one could not have been blue because of the rule. But anyway, this could have been blue. Now, let's fix our attention on any one of these color configurations. And I'm just because I have drawn the blue red, I'll go ahead with the blue red. Okay. So now what we are going to do, we are going to go inside this and we're going to look at the triangles and we're going to see how many blue red edges does the triangle have. Okay. That's a simple thing to do, right? We go inside. There's so many triangles that have been formed. And looking at them, I'll count the number of blue red edges. By blue red edge, I mean an edge which has one vertex red on one side and one vertex blue on the other side. And okay, so I'll count that. That's fine. But what do I do with it? Now, here's the ingenious part of this problem. What we are going to do, we are going to transform each of these smaller triangles into a node of a graph. So, and by a graph, for those who are not familiar, I don't just mean a plot on the XY axis. So, a graph is simply a collection of entities called nodes. I'm going to call these nodes, and some lines or edges between them. This might represent some kind of relation or connection between these. So these guys I'm going to call nodes. If I can get my cursor to work, yes. So these are guys I'm going to call nodes. And these guys I'm going to call edges. Edges join nodes. So actually, this is pretty standard nomenclature for graphs. So what I'm going to do, for each triangle, I am going to consider or map it to a node in some graph. So this here is some node. This here is some node in the graph. This here is some node. Same for each of these smaller triangles. Now, what am I going to do with the nodes? Okay, let's see. The number of edges coming out of a node and going into the other node is basically going to be equal to the number of blue red edges. So, for example, let's look at maybe this small triangle right here. I'm going to draw an arrow right here. Oh, actually, coincidentally, we have found one with three vertices of three different colors. Need not always be the case. And let's maybe not look at that one. Maybe we can look at this one. So here we have two green vertices and a red vertex. Okay, so I'm going to map this triangle to a node in my graph. And how many blue red edges does it have? Actually, it does has none. So this guy will not have any edge coming out of it. Similarly, if I were to look at maybe this one, this triangle right here, this has the one blue red edge coming out of it. So it just has the one edge coming out of it. Now, at this point, maybe you can pause and reflect, pause and think. For a triangle, which is also a node by the way now, how many edges actually can come out? Can I have no edge coming out? Well, we have already seen that case here. So when does a no edge situation arise? A no edge situation arises when the original triangle, which represents this node, does not have any blue red edge. And when can that happen? Well, that can happen when either you have a green, 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 or you have a green, red, green. And it's actually pretty straightforward to think of other combinations as well. But the important thing is that it is possible to have a node which has no edges coming out. So this is the number zero, by the way, zero edges coming out. Okay, is it possible for any node in our graph to have one edge? So by that, we mean an original triangle in the problem which just has one edge, which is red blue. But wait, if one edge is red blue, what about the others? So it has to complete a triangle actually. After all, this has to be a triangle. So what has to be this color of the node here? This vertex, well, it cannot be red because if it's red, then we suddenly have two red blue edges. Can it be blue? Again, it cannot be blue because again, then we will have two red blue edges. So then it has to be one. Oh, sorry, it has to be green. And only when we have the green vertex here can we have one edge coming out of the node to which this triangle has been mapped in our graph. And in fact, the red, blue, green triangle, the elusive triangle in whose search we are in, is the only triangle who will have one edge coming out. Okay, so it is possible to have a triangle that has one edge coming out. Is it possible to have triangles with two edges coming out? Yes, it is, right? Because we just saw if I have a red blue edge, and if I either place a red here or a blue here, we get two edges suddenly. And is it possible to have three edges? No. The node will not have three edges ever. In fact, it will never have more than two edges because it's physically not possible to have more than two red blue edges in a triangle. Okay, so now let's forget about the triangle, this triangle, for a bit. And let's concentrate all our effort on this graph that we have drawn. So it's a graph which has so many nodes, each node corresponding once again to each of these smaller triangles. The smaller the pieces, the more the pieces, and the more I have these kinds of nodes in my graph. And I also know that each node can either have no edge coming out of it, can have one edge coming out of it, can have two edges like this guy coming out of it. And maybe, who knows, maybe there's a node which has three edges coming out of it. And this is what, oh, I'm sorry, I made a boo boo. There cannot be, let me take this back. There cannot be any vertex which has three edges coming out of it. And our job is to find out or prove there is always in this kind of a graph, there is always a node which has one edge coming out of it. And how do we prove that? To do that, the guy who actually made this proof or gave this proof actually did something very non trivial, and I think which lies at the crux of the solution, which makes it completely non trivial and completely surprising. So, what he said was, I am also going to, in this mapping of triangles to nodes and triangles to graph, I am going to consider a special node. And this node, which I'm just going to mark here, is also a part of this graph. But this represents the outer world. And by outer world, we mean this part here. And we're going to see how many, the rule is still the same, by the way. So each of these smaller triangles which have an edge lying on the edge of the outer triangle, obviously they share an edge with the outer world. So once again, if there are a red blue edges being shared by the triangles that have been formed inside by breaking the original glass pane, if there are any red blue edges being shared with the outside world, then we count the number of edges, and those are actually going to be the number of edges coming out here in the graph from the node, from the special node which denotes the outer world. So if you look at the figure here, by the way, there are going to be no red blue edges on this outer blue green edge. There are not going to be any blue red edges on this outer red green edge. The only blue red edges are going to be here. And that's because the problem dictates us. We could not have colored anything green here. So in fact, all the edges that are going to be here are going to be either red blue, or they could even be red red, like this small guy here, or it could even be blue blue. So how do we count? Actually, we don't want to exactly count. We are only interested in the parity. We're only interested if there are odd number of edges or even number of edges. And I hope you see, but because we started off with a red guy here and we ended up with a blue guy here, we could only have an odd number of red blue edges. In other words, whenever we start with a red here, we can only have odd number of switches, so to say. And by a switch, I mean suddenly red becomes a blue, blue becomes a red, then somewhere down the line, a red has to become a blue. That's a switch. So if you started off with red and you ended up with a blue, you would have had to make odd number of switches, and that implies that they're going to be an odd number of red blue edges which are in contact with the outside world. So we also know that this guy here has an odd number of edges. And this is now what we are going to do. Now we have everything we need about this graph. We have so many different nodes. A node can have no edge. A node maybe has one edge, which is the elusive node we are in search for. Or a node can have two edges. Or there is this one special node for which we definitely know that it's going to have an odd number of edges. Okay, sure. So what do we do with this information? Well, we just go ahead and simply sum up for each node. So let's say I is a node. I'm going to sum up d of I. So in graph theory, d just means the degree of a node. And the degree is simply the number of edges that come out of a node. So the degree of this guy here is 1. The degree of this guy here is 2 because there are two edges coming out. So we are going to just go and look at this graph, go to each node and just add up the number of edges. So we get the total number of the total degree of each of the node in the graph. So the degree for this guy is 0 here. Seems it's 0 here because I've not completed the graph. It's 1 here, 2 here, 2 here. I'm going to go ahead and add all of this. I'm going to get a number. Again, I'm not interested in the sum. I'm interested in the parity. Now, if you realize, and this is a standard result in graph theory, maybe I'm going to skip ahead and give you an option to pause and see why this is true. But if you sum up the degrees for all the edges, for all the nodes in a graph, you will always end up with an even number. It's always 2 times something. So maybe you want to pause and see why this is so. And I'm going to continue in meanwhile. So what is this something that is 2 times the 2 times of which is the sum of the degrees? Well, if you think about it, look at this node here. This node here, when you're counting the degree, you count the contribution of this edge. But when you come here, you also count this edge because it's coming out of this node. So, in some sense, for each edge, you are counting its contribution twice. And that's precisely why this is just 2 times the number of edges in the graph. Again, not interested in the sum, I'm just interested in the parity. Now that I know that the sum of the degrees of each of these nodes is an even number, let's come back here. We see that this guy, this just one node, which we are guaranteed has an odd number of edges. Okay, so let me subtract that. So this summation over all the nodes. What if I just uh, subtract the degree of this guy? I'm left with the sum of the degrees of all of the other nodes, right? But here we have an odd number. Sorry, here we have an even number, and I subtract an odd number. I'm supposed to get back an odd number. So what that means is that if I forget about this guy, the sum of the sum of the degrees of each of these vertex must also be an odd number. But we know that the sum over the degree of each of these vertices can either be 0, 1, or 2. Well, 0 contributes to even parity, 2 contributes to even parity. But we are adding up some number of zeros, some numbers of ones, some numbers of two, and the result we are getting is we just proved the result that we're getting must be an odd number. So there has to be a 1. There has to be a node with degree 1. In fact, what we have proven is something stronger. There has to be an odd number of such nodes. Let that sink in. Yeah. So there has to be an odd number of nodes in this graph which have a degree of 1. And again, if we transform back to our problem, that just means there have to be an odd number of triangles which are inside, which just have one blue red edge, which again implies that they have 3 vertices of different colors. This is interesting and it's such a counterintuitive proof. The mapping of the mapping of triangles to nodes. And again, even if that were somehow kind of obvious, it wasn't to me, certainly, still isn't to me. I think it was a stroke of genius to think about the outer world as another node. And yeah, that just solves the problem. That just gives us the last missing ingredient. This guy here, this extra node which represented the outer world, gave us the last piece of the puzzle which helped us in arriving at the parity, and the parity essentially helped us solve the problem. I think this was nice, and I love share talking about this to whoever I can, and whoever would listen to me. Okay then, thanks guys.